And hello everyone on YouTube. Welcome back to our discussion on turbulence modeling. Today we want to talk about the Spalart Allmaras turbulence model. These guys, this model was developed for aerodynamic flows, mainly for aerospace applications. There's Stephen Allmaras. He's from MIT. He was from MIT. I don't know where he is now, but yeah, there's Felipe Spalart. I don't know how to pronounce their names right, but he's from Boeing. Okay, so this is where you can find the scientific paper for the model on ResearchGate. The text is for free. You can just download it, and you'll be able to access the paper. So this is available online, at least at the time I'm recording this video, April 2020. It's available. I hope it'll still be available in the future, but without further ado, let's get on with it. So why do we want to study this Spalart Allmaras if we have the K Omega SST, especially if you looked in the video series and you saw the K Omega SST? Well, two reasons. One good thing is that it's a pretty simple model, because you're not solving for K and omega, the transport equations, okay? You only solve directly for the kinematic viscosity, so to speak. K omega, okay. Yeah, you're not solving for turbulent kinetic energy and this dissipation rate. Yeah, you're not solving for this turbulence, kinetic energy and dissipation rate. You're solving instead directly for this turbulent eddy viscosity. Alright, so if you look at the CFD online page, you just see this equation and not a lot of explanation. So this video is just here to roughly try and explain what this Spalart Allmaras model is about and how you try to formulate this, so at least you understand what all these terms are about. So here's the reference on ResearchGate, and the citation is here. I think Dr. Aiden has another video on this, Fluid Mechanics 101. So he's a good reference as well. He gives a good reference as well. And what is this? What did I paste it here? Okay, so this is an improvement to the Spalart Allmaras turbulence model. It's a follow-up paper. I'll just leave it in the reference as well. Not important for this video. Okay. So from this paper, you see it here. This is I mean, it's free. It's online. You can download it, I think. Yes, so if you download it from ResearchGate, you will see something like this. Okay, so it won't be as nice, but I mean, all the stuff is here. You cannot use you can't use the search function as well. It's like a photocopy kind of thing, but all the information is here. All right, all the information is here. Okay, so I'll go through it one at a time. All right, so remember, we're trying to develop a transport equation for eddy viscosity directly. So the advantage here is that it's easy to use, because you don't have to think up of so many boundary conditions, and the computation cost is relatively low since you have one more transport equation. So here's the derivation or thought process when they develop the model. Okay, so that's what happens in this paper. So the closure model. First thing is the closure model. How do you model the Reynolds stresses? So you see UIUJ bar. Okay, it's given by 2 nu t into Sij, which is the rate of strain, the strain tensor. Okay, so this is actually what we try and solve for. Okay, so we try to solve for this term, this turbulent kinematic viscosity. And if you recall from previous videos, that turbulent kinematic viscosity is given by these terms in the k epsilon model. So it's c mu into k squared over epsilon, or c mu times k over omega, or k over omega star if you define omega star differently. So how I define omega star? Okay, omega equals to, or if you see in literature, k over epsilon. So this is just a refresher, and omega star is equals to omega. Okay, omega equals omega equals to omega star c mu, or sometimes they'll use beta star in the CFD online website. So that is how we define it. So this is our friend, yes, turbulent kinematic viscosity, otherwise known as diffusivity. So to construct the equation, okay, we look at this. We always have our first terms. This d, the substantial derivative, d nu t over dt. So this is the substantial derivative on the right hand side or left hand side. So this is the time dependent term, and this is the convection term, or advection, however you want to call it. So if you look at the CFD online, you'll see it on the left hand side as well. Okay, nothing too new here, because like any other property, it's time dependent, and the fluid will carry it along everywhere. So what's on the right hand side? That's the more interesting part. So firstly, we need source terms and destruction terms, and source terms and destruction terms. So yeah, we'll have a source of turbulent viscosity. Okay, I'll spell check this. Oh, yeah. Turbulent means stormy, confused, or violent. So confused viscosity. Anyway, yeah. It's an interesting thing I note. Confused viscosity. So yeah. Anyway, okay. Anyway, this is a pun joke in there. Anyway, so remember turbulence viscosity. Back to our discussion. Remember, turbulence viscosity has its source in the strain rate. And I'd like to bring you back to the dimensional argument. Like, okay, if let's say we have a velocity profile like that, okay, it's a mean velocity. All right, so if we just take a look at these two layers and blow it up, so what you have is a layer with higher velocity and a layer with lower velocity, right? So this is near the boundary layer, near the wall. Okay, so there's a U2 here and U1, and if you think about it, this almost looks like a flat plate flow. That's how I kind of described it. I didn't make it so clear. This looks like flat plate flow, with the top plate moving at U2 and the bottom plate moving at U1, right? Where U2 is greater than U1. Though of course it's important to note that the relative velocity is actually the one that matters. So you could just as easily say the bottom plate velocity is 0. Okay, 0 meters per second, and the top there's a velocity of U2 minus U1. So it's the difference in velocity that matters. Okay, so delta U is the characteristic velocity. So remember why we said turbulence comes about from this gradient in the velocity, which is du dy, right? Turbulence comes from here. Turbulence comes from here, and the argument was this: if we try to have a characteristic Reynolds number for this system, which is like this flat plate system, this characteristic length scale will be delta y, and the characteristic velocity is delta u. All right, and the viscosity term is just nu. So if we have the Reynolds number, which is kind of a measure of the turbulence, if you think about it, so it's delta u, delta y over nu, right? It's u into a length scale over the kinematic viscosity. And if you remember the last time I was talking about how delta u can be written as du dy, okay, du dy into delta y, right? So you could just as easily write like this, delta u delta y squared over nu. So given that this is fixed and this is fixed for a given fluid, and this is fixed for, like, you know, you just fix it because given your length scale, no, it's not the length scale, this is just you fix your point of reference, your length scale of reference anyway, because you want to compare between two layers of fluid, and the distance between the two layers of fluid you kind of fix here. So these two are fixed. So in effect, okay, Reynolds number, it kind of proportional to this strain rate du dy, and so this actually increasing this will increase the Reynolds number, and that will sort of produce turbulence, if you think about it like this. So this is the dimensional argument, right? And on a side note, I think in the earlier videos I said S and omega was similar in meaning in the last video or last few videos when I talked about the K omega SST, but they're not. I mean, the terms contained in both of them are similar. I'll give you that. But Sij is the strain rate tensor. It measures the rate of deformation of the fluid, and S equals to square root of 2 Sij, which this is the strain rate, and this is more to do with the velocity gradients, this du dy in 3D. And this omega ij is not exactly the same. While you see this velocity gradients here, this is actually more to do with the curl or vorticity. So recall that the vorticity, the curl omega, this is a different omega from this omega here, just beware. Okay, this omega, the vector omega, is the curl of the velocity, is the square root of this big omega ij. So this tensor here kind of measures the tendency of the fluid to twist or curl around or rotate. Okay, so anyway, how can we write a source term? The source term it's written as follows. You have a basic you have a constant there, and in the paper, in this paper here, yeah, subscript B stands for basic. So this is our basic source term, and in most of the fluid, yeah, we'll use this source term as the rate. I mean, this is how quickly this turbulence viscosity is being produced. So turbulence viscosity, I mean, it measures how much turbulence there is in the fluid, so that shouldn't be too new to you. Okay, S is this rate of deformation, which is the 3D version of du dy. If this is the 2D version, because it has u and y, the 2D version, the 3D version will be S, which is equals to half, all right, okay, half into all the terms here, which I'm not going to write out, but I typed it out here. Okay, del ui del xj plus del uj del xi. So this is rate of strain, the strain rate tensor. So this is the rate of deformation in 3D. Okay, so next term. So okay, this is where the source term comes about. Next term is the diffusion. So just like in K omega SST or other models, there's always this diffusion term here. Alright. But there are extra terms that pop up in the diffusion term. Question is why? Right. So from let's say this part, okay? Yeah, this part is where we see the diffusion term. Where is it here? Yeah, here it is. The diffusion term is here. So we have this nabla or del of nu t into del of nu t. Now this is a divergence of nu t times the del of nu t, which is the turbulence viscosity term. This is quite analogous to what we have here, the diffusion term here. But there is this extra term. Okay. There is this extra term that pops up. This is CB2 nu t squared. Why does this thing come about? Well, if you follow the arguments here, it says here, manipulations of the two equation models often bring out diffusion terms that are not conservative. For instance, cross terms between the gradient of k and the gradient of epsilon. So by analogy, and to acquire a degree of freedom, a non-conservative diffusion term, which is the second term. So what does that mean? That means basically, remember our k and omega equations, right? Okay, so let's try and remember, okay, this is omega star. I'm using omega star to write this. This is from our K omega SST model. And remember omega equals to beta star omega star. That's what I used. And remember how turbulence viscosity is described for that model. It is K over omega star. And let's say you wanted to derive an equation for the kinematic viscosity from these two equations. How would you do it? So firstly we kind of try and have our equation like that. I'll make k the subject of this equation. Okay, so k equals to omega star times nu t. So at least we have an omega star term and a nu t term here. So now nu t can be put into a transport equation. So what I did here is to just substitute these terms into the k equation here, right? And then I'll get this. So this is k, this is k, this is k, and this is k. So that's where I substituted. So try differentiating every way. Try differentiating it every day and subtract. Afterwards, there'll of course be terms dealing with the omega side, and you try and subtract it out later on, but we can see what happens to the viscosity term after that. So let's go term by term. Okay, or rather, okay, maybe I'll skip it because it's a little, complicated. But basically, you try to get all these out. And you see this viscosity term here. Just focus on this. The rest of it you can just ignore for now. All right. How would you differentiate this term? Firstly, I will do this. Okay. Omega star partial xj plus omega star partial nu t partial xj. All right. So that's the first part. All right. Okay, noting this, we'll have this thing here. Okay, and immediately you will see some complications happen already. So let's see. Now these are two terms we have here. All right, these are two terms we have here. One term looks like this. Okay, so what I'll do is just delete this one off here, and then here I'll just delete the second term. Alright. Okay, so it looks like we'll need to do more differentiation here, and it's about to get a little bit messy. So let's simplify this part. We can do like so. New. Okay, assuming this doesn't quite change, or yeah, maybe I'll just keep it in there. Yeah, I'll just keep it in there because I don't want to touch it. I'll have this. Okay, I'll bring the omega out instead, so that's easier. So I'll have this inside. Just a simple product rule again, and you have a plus. I'll have this outside. Then I can delete this term. Okay, can delete this term, and in a sense you'll see this term popping out. Okay, so this is what we kind of expect, but this is one of the extra terms that pops up. Likewise, we'll have another term here. Okay, another term here, and that will be equals to nu t into this nu t into this plus del omega del xj into this. Alright, so we see that this simple innocent looking term actually becomes 4 terms at least, right? Equals all of this plus all of this. Yeah, so all of this plus all of this. Okay, of course there will be lots of simplification, but you'll notice one thing. If you notice this term here, it actually has a nu squared dependence. See, del by del xj, and you have a nu squared, so it's equals to nabla of nu t squared, because in the turbulent region, so okay, you have some constant times this. So in the turbulent region, okay, the turbulent kinematic viscosity is much bigger than the normal fluid turbulence. So in effect, this term can be approximated as such, a constant times the divergence of nu t squared, or else it will, it looks like this. Okay, some constant times this term here. Okay, it's a nabla. So if you actually wonder where this nu t squared terms come from, this could be one of the way you can reason why there's a nu t squared term, why there's an extra, dissipation term, so to speak. Yeah, so if you're wondering, yeah, this nu t squared here, some constant outside, it probably comes from, if you try to combine this k and epsilon equation together. So this is where this term kind of pops up. This is one of the reasoning you can use for yourself. Okay, so I'll stop for now because we're about 20 plus minutes in. Next video I'm going to continue more on how it is being derived. Okay, thanks for watching. I'll see you guys again. Bye bye.